Hello there. Today we'll be doing number 62 of our Neetcode 150. This is a validate binary search tree. In this particular problem, we are looking at a valid binary. We're looking at binary search trees and validating them. So, what exactly is a binary search tree that's valid? So, there's an example where everything to the right of this binary search tree has to be greater than 2, and everything left of the binary search tree has to be less than 2, and this makes it valid. However, if we go to the right and we see something smaller, well, this is false because the right side must be greater than this particular item, the parent. But there's some edge cases that we need to ensure to take care of. That edge case is well, excuse me. So the edge case is suppose any item on this entire tree on the right side must be greater than 5. It just must be greater than 5. It cannot be greater. I mean, anything smaller than 5, no good. So how do we keep track of that? And everything to the left of that 5 has to be, well, smaller than 5. It just has to be smaller than 5. So how do we make sure that happens at every stage? Well, we create a check. So that basically means we take a valid and we take a root and a left and a right. So what happens if there's no root? Well, we just return true. It's a valid. That's a valid binary search tree. If the root dot val is less than or equal to the left side, or the root dot val is greater than or equal to the right, then we return false. Now, what do I mean by left and right? So that means this is our minimum, and this is our maximum. So maybe we can do this and maximum. So instead of that way, maybe it's a little bit clearer. So what is our minimum? Our minimum here, when we go to the left side, is going to be 5, and when the maximum we're going to go to when we go to the left side is 5, and the minimum we need when we go to the right side is 5. So else return a valid root. When we go to the left side, what do we change? When we go to the left side, we have a maximum number. So this stays as the minimum, and the maximum changes. If it's greater than this number, then it's no good. So we have a maximum number now. We cannot exceed. So valid root dot right, and we go to the right side. There's a minimum number that we cannot be below. So that would be root dot val, and that would be the maximum. And what do we do? So we return the valid of root, and the minimum is going to be well, float of infinite, because there's no bound about how small or how big it can get. So there is no minimum, and there is no maximum number that we need. So let's run. And it is valid, and let's submit. Okay, we got a pretty okay answer here, and I think that is a pretty good answer. It was a little faster earlier. Well, it was a lot faster earlier, but now it's become a lot slower. but this is the code that we need to ensure that we know. So every layer that we go down, we are changing the maximum and minimum value possible for this variable. So for 1, the maximum number that we can have is going to be 4, because anything that is equal to or greater than our max number, which is 5, will return false. So it has to be a 4 or below. And when we go to the right side, it has to be greater than our minimum number, which is 5. It has to be 6 or more. And we keep it inbound when we go to the left, and we change basically every time we go to the left, we change the maximum number that we cannot exceed. And that's how we can think about this problem. Another way we can think about this problem, which might be a little bit more intuitive, is that we can change this to left and right. Now you might be thinking, this left and right thinking, how is this like more intuitive or less intuitive? You're thinking, well, what are you talking about? Like, how can this be more intuitive? So the more intuitive side is, oh, we're going to the left side, right? That means the left side. That means we're gonna have to change the maximum number, which is on the right side. And when we go to the right side, that means we have to change the left number to be root.val, which is our minimum number. So that's another way to think about it. It also runs all the same, but I mean, it's just a different framework of understanding the problem. Again, this is really weird. It's just a lot faster now. Maybe just because the wording. Maybe if we just change this to L and R, maybe that will make it even faster. I don't know. Possibly. I wouldn't put it past myself. I mean, I don't know what the heck I'm doing. I'm just trying to learn here, and maybe let's run the code, and maybe we'll see something that we don't usually see, and we understand something that we never understood before. Oh, and then there's no correlation at all. Anyways, it was easier to understand one with the left and right. So there are many ways to understand the problem and frame a problem so that we can understand it better, and we should frame it the way that helps us understand the problem the best, and allows us to give the best explanations for a coding interview to ourselves, and so that we can better remember it and even explain the problem. So that's how you identify valid binary search trees, and we're checking every node to be a valid binary search tree by checking by using its parent information, by holding that by caching that in our call function. Very good problem. I highly recommend it. I think there's a lot to learn here. And if you have any questions, please comment below. If you enjoyed the video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and have a good one.